Okay, in this video we're going to apply the little bit that we know now about inverse functions to some examples that you're going to need to solve in your homework and on quizzes and tests and so forth. This first example is kind of your most basic. It says find the inverse relation for the following relation, and you just have a table of values and you have your inputs x and your outputs y. If you want to find the inverse, basically all you're doing is you're taking the outputs of your original function and making them the inputs of your new inverse function. So if you had to create the inverse relation, so now this is the inverse over here, right? So just keep that straight. If this is the inverse, now the x values are simply all of these original y values. So the inputs are going to be -3, then we're going to input 4, then we're going to input 6, and then 0, and 5. And now the outputs, y, for the inverse, are the corresponding inputs from the original function. So if we were to plug in -3 in the inverse, it would map us back to that -2, the original input for that output. If we looked at 4, it would be mapped back to -1 in the inverse. If we were to plug in 6, it would take us back to 0. If you plugged in 0, it would take you back to 1. And if you plugged in 5 into the inverse, you would go back to the original x value of 2. So notice, at the end of the day, all we really did was switch x and y. I mean, it's really as simple as that. And there's your inverse relation. One thing that's really important to note, that's going to kind of come back over and over when we talk about inverse functions, is the following: the domain of the original function f. If you think about that, now that domain, remember, was all of these guys, right? This is your domain of f. It really turned out to be the range of the inverse. So the domain of f turns out to be, it is the range of the inverse, which, remember, the inverse notation that we use is f inverse of x. And now remember, that doesn't really have anything to do with an exponent at all. It's just notation. That's just the inverse function of f. So the original domain of the function is the range of the inverse, and likewise, if you took a look at the original range, or the outputs, that becomes the inputs for your inverse. So everything gets switched all around when you do these inverses. So the x and y get switched, and what I'm telling you is that the range of f, let me rewrite that got scribbly, we're in a hurry. The range of f is the domain of the inverse function. Okay, so that will come into play a little bit later on when we start looking at the domain for these inverse functions. Let's take a look at another type of example that you'll have to do. What I want you to do here is, let's find the inverse equation. So find the inverse equation for each of the following. We'll call this example 2. Y equals 2x minus 5. Now keep in mind, you may get problems where it'll just say y equals 2x minus 5. Don't freak out if you see f of x equals 2x minus 5, right? They're really the same thing. Y and f of x are both just the outputs of the function. So if you want to find the inverse, the key is just to do what we essentially did in the last example, which was switch x and y. So all I'm going to do is switch x and y and solve for y. So if I take that original problem and I switch the x and y and write x equals 2 times y minus 5. Now if you think about it, what we just did should kind of make sense. What we want to do we want to plug in for our inputs now. Instead of inputting the x values, which were the original domain, we want to plug in the original domain's outputs, the y values for our function. And x will be what we get out. What we just have to do now is solve for this y. So if we do that, we're going to need to add 5 to both sides, and we get x plus 5 equals 2 times y. And our last step would be to divide everything by 2, right? So I can divide this whole side by 2, and I would get y equals x plus 5 over 2. Now, what we just found is our inverse relation. You could write it like either y equals x plus 5 over 2, and of course, we could divide each term by 2, so we could write it as y equals x over 2 plus 5 over 2. Right? These are both the same thing. Note the following though. Since these are the inverses, I really shouldn't write y anymore. This would be f inverse of x. This is our inverse function, so we can write our, for the second notation, f inverse of x is x over 2 plus 5 over 2. And we've just found the inverse function. In our next example, I'll show you how we can actually verify that these do, in fact, undo one another, so to speak, and are inverses. Let's do one more example where we find the inverse equation. Oops. Here we go. Let's do the same type of example. Let's find the inverse equation. So let's do for this one something a little bit more fun. Let's do f of x equals 2 times x to the third minus 1. Now remember, f of x is really just y. So that's really like y equals 2x cubed minus 1. If I had to find the inverse, I'm going to just switch out the x and the y and write x equals 2y cubed minus 1. And now I'm just going to solve for y. By adding 1 to both sides, I'll get x plus 1 equals 2y to the third. Then I'd need to divide everything by 2, so I'd get x plus 1 over 2 equals y to the third. And of course, the last step to get y by itself is I'd have to cube root both sides. Now I luck out because cube rooting does not require the plus or minus. There's only one root for the cube root. So I'd have the cube root of x plus 1 all over 2 for my inverse function. So my final answer, I would write f inverse of x equals the cube root of x plus 1 all over 2. And now let's take a look at the final thing that I'm going to show you in this video, and that's going to be verifying that two functions are inverses. Now let's talk about how we can verify that two functions are in fact inverses. So let me kind of split off this side of the board. If I want to verify, so we're going to verify that two functions are inverses. What we're going to do is compose them. So let's take the example that we just did. We had, in that previous example, we had f of x equals 2x minus 5, right? And then we found that the inverse function, f inverse of x, is, what did we say it was? I think it was x plus 5 over 2. So what we're going to do to kind of verify that these are inverses is compose the two. Meaning I'm going to plug one function as in for the input for the other function, and it's kind of interesting what happens. Now keep in mind, f of x is a function that takes an input and multiplies it by 2 and then subtracts 5 from it. the inverse undoes that function. So what it's going to do is take the input, add 5 instead of subtract 5, and then divide by 2. Something very interesting happens if we compose them. So what I'm going to do is I'm going to do f of f inverse of x. And let's see what happens. Now, remember, when we compose, we always rewrote the outer function with the input box. So in this case, it's going to be the function f. So I'm going to write it as 2 input box minus 5. Now, in the input box is going to go f inverse of x, which is x plus 5 over 2. So what I have really is 2 times x plus 5 over 2, take away 5. Well, 2 times x plus 5 over 2 is really 2 over 1 times x plus 5 over 2. And if you think about it, since 2 is a factor of that numerator, I'd have to multiply it to x plus 5 and then divide by 2. I can cancel those. So I'm left with x plus 5 minus 5, and you get just x. So we've just shown that f of f inverse of x is just x, which should make sense because what we've done is we've plugged the function that undoes the original function's operations in, so ultimately we end up with just our input back, which is x. Let's see what happens if we do it the other way around and we do f inverse of f of x, meaning I'm going to plug the original function f of x into the inverse. If I do that, now the outer function is f inverse of x. So I'm going to rewrite it with a box plus 5 over 2. In the box goes 2x minus 5, the original function. If we simplify that, all we have is 2x minus 5 plus 5 all over 2. This one simplifies pretty easily as well. If negative 5 plus 5 cancel, giving you just 2x over 2, and you get just x. So we've just shown that f inverse of f of x is x. We've just verified that f and f inverse of x are in fact inverses, and that in fact should always be the case. So the moral of this story is, if f of x and another function, let's say g of x, are inverses of one another, then it has to be true that f of g of x, if we compose it that way, we should get x. And it's got to be true that if we did g of f of x, we should always get x. This is called verifying functions are inverses. I'm going to do one more example with you guys about verifying functions are inverses with the kind of tricky one that we did for the second example. If you remember our second example, I gave you f of x was the function, I think it was 2x cubed, take away 1. And then our inverse function, I'll just call it g of x right now, our answer was the cubed root of x plus 1 over 2. What we want to do is verify that this function f of x and this function g of x are inverses. Well, that means I'm going to have to show that f of g of x equals x, and I'm going to need to show that g of f of x also gives me x. So let's see if we can do it. The outer function in this case, in this composition, is f. I'm going to rewrite it as 2, and instead of x cubed, put a box cube, take away 1. Now inside of that box we're inputting g of x, which we know is the cube root. It's the cube root of x plus 1 over 2. So what we have here is 2 times the cube root of x plus 1 over 2, and we're going to cube it, take away 1. Guys, if we cube this cube root, they undo one another. right? If you cube a cube root, they cancel. We're going to end up with 2 times the quantity x plus 1 over 2, take away 1. Since I'm multiplying 2, it's the same as 2 over 1, times that fraction, x plus 1 over 2, these 2's cancel, and I get x plus 1 minus 1, and I get just x. So far, so good. Let's take a look at g of f of x. Now my outer function is g. I'm going to input a number, or in this case, f of x, plus 1 all over 2 inside of the cube root. So again, I rewrite g with an input box in for x. Now we're going to plug in the function f inside the input box, so 2x cubed minus 1. So what we have to do is the cube root of 2x cubed minus 1 plus 1 all over 2. Well, I can do negative 1 plus 1, those cancel, so I'm left with the cube root of 2x cubed over 2. I can divide the 2's out and those cancel, and I get just the cube root of x cubed, which is just x. Now, I will say this, what some students do is they know at the end they just need to get an x and an x, and so they may start off with that step and then kind of magically end up with just an x. And some of they'll just go like this and cancel everything out and then just put an x without showing any work. And that's not going to work. You want to go step by step so I can see how you simplify using the correct order of operations. You wouldn't want to just go, oh yeah, these things cancel, and oh, the answer I know is x. I will not give you credit. You need to make sure you show me how we can simplify step by step by step, and I know you're doing the right order of operations. I would like you now to try the first couple self-quiz problems that I asked you to do in class for homework, and have that ready for tomorrow.